Hi, welcome again. So, continuing our hardware-centric track, we have Katherine Scott. She's the lead developer for Tempo Automation, and she's here to give us a crash course on the Internet of Things. So let's give her a hand.
Hi, guys. So a quick and dirty guide to putting things on the internet. You guys having fun? Was it a good day? Did you learn stuff? And it's the end of the day, so we're going to have a ton of fun again. All right. So as I see it, I wanted to write an intro sort of tutorial where I talked about how to do different stuff with hardware. And part of the problem is when you go and look at sort of all the tutorials out there, there's a bunch of tutorials on how to do little tiny toy things with hardware. And there's lots of tutorials about how to do web stuff. And that's because people tend to break off into these camps, right? There's people who do massive web scale stuff. And then there's people who tend to build more hardware stuff like robotics and computer vision. And that's what I do most of the time. And you know, every time I go and build a robotic system or go and build some piece of hardware, almost immediately, as soon as it's done or as it's being built, it's like, well, can you go give it a web interface? Can you go do something with it so I can see it through the internet? It's like, yes, I can, but I got to figure it out. So I wanted to write like a really simple introductory experience for building something like that. How do I take a simple object and connect it to the internet? So part of the problem is that you have to figure out what you want to put on the internet. And stuff that sells really well is stuff that deals with pets. So I decided to put pets on the internet. And I don't have cats, and I don't have dogs. I used to work in a neuroscience lab, and I kind of fell in love with rats because you can leave them for a week, and they have all the best qualities of dogs and cats, and they're compact and easy to deal with. So I decided to put rats on the internet, which is great because rats support all sorts of wireless protocols and interface standards, and you know, they're super easy to wire up. Oh, wait, they are totally not easy to wire up on anything. They have no standard interfaces except for one, and that standard interface was thought up by this Harvard psychologist, and his name was B.F. Skinner. And so B.F. Skinner's whole bag was he's a psychologist, and he wants to train animals to do tasks so he can see how they perform those tasks and how they change when you change sort of their environment. And so he built this thing called a Skinner box. It's also called an operant conditioning chamber. And so the Skinner box, you guys may be familiar with this from work, is that it's either a light or a buzzer, and the rat is supposed to hear the light or the buzzer, and it's supposed to respond to that by pushing a lever, and then it gets food. And there's sort of a other way that you can train rats, where you electrify the bottom of the cage and you shock them, and then they push the lever, and then you stop the electrification. I wasn't going to do that because that's not cool. So from these sort of just basic conditioning, you build up primitives to do real science, to do real biology and do real neuroscience, and you can also just play with your pets. So I went to go buy one of these things, and they're $10,000. I'm not even kidding you. It's a lever, a buzzer, and a computer. It's $10,000. This is the quote I got for doing this. And this is actually like a huge problem because like the NIH and the NSF pay people to do research like this. And you can't just have one rat. No, you have to do massive parallel rat testing at scale to get your drug through. So you're looking at like tens of Skinner boxes. So I decided, well, shoot, I can do this for $100. And I totally did. And it's super cheap to do. Last year, if you were at PyCon, everyone got a Raspberry Pi. You know, you can get a Raspberry Pi for $30. I got a Raspberry Pi IR camera. So IR is kind of like night vision. It's like the poor man's night vision camera. And that plugs right in the Raspberry Pi, $30. A couple of metric bolts. It's a couple bucks at the hardware store. A $5 cheap stepper motor, a resistor, a buzzer, and a little chip called an LN2803, which is like a stepper driver motor. All it does is takes little signals that have not a lot of current and make them into big signals with lots of current and a switch. And then a lot of really awesome 3D printed parts. So I had a friend from the internet help me do some mechanical design, and we basically started building the bits of a Skinner box. So there's a food hopper, and the food hopper basically distributes treats to the rats. There's some mounting brackets to hold it up to a rat cage. There's a lever and then just a simple mount for the camera. And this all goes inside a Tupperware I took out of my kitchen. And so inside the Tupperware is where I mounted all the hardware. So the hardware is super easy. It's just a Raspberry Pi, a breakout board, and this controller circuit, a couple resistors, switch, and a buzzer. And so then you mount it all and you deploy it. So you have to deploy hardware just like you deploy software. So I deployed it with my pets and wanted to see how they would do. So once the hardware was built, it's like, well, how do you build the software to interact with it, right? And not just interact with it, but interact with it over, say, your cell phone or over a web browser versus just like running a simple script. So first you kind of spec out what you want to do. So what did I want to do? I wanted to display the images on the camera, record the activity over time, be able to remote control feed the pets. That's a big seller, right? And then I also wanted to run and record actual science experiments where I buzz the buzzer, the rat responds, it pushes a lever, and I record whether it did so correctly or not. And finally, I wanted to display all of those results in something I could digest, so like a daily digest of the results. So to do all this, I kind of went through and figured out what tools from the Python ecosystem I could use. So to run the motor and the buzzer and the switch, that's simply GPIO library from Raspberry Pi and a thread. To run the camera, I just used a library called PyCamera, which is just a simple Raspberry Pi camera interface. OpenCV, which is a computer vision library, and NumPy, which is a numerical processing library. To run the experiments, I have NumPy, which just does some analysis, Mongo, which stores all the data in matplotlib. You can build Mongo on a Raspberry Pi. I'm just going to warn you, it takes like 12 hours, and it doesn't really work well, but it does run. And then finally, to display everything, I just used a simple Python bottle app and some Bootstrap and a couple of WebSockets. So roughly, how does this all work? So from an intro perspective, how do you put all these parts together and make them interesting? So you start off by building the hardware interface, which is just a thread running, and you create a couple methods to get into that thread and say, hey, run the motor enough to feed the rats. Hey, has a switch been pressed? Similarly, you build a camera interface, and its entire job is to run in a thread, grab an image once a second, and then I actually wanted to monitor activity, so I diff the image, like I do some image processing where I diff it from the last image I received and see if I can measure the activity of the rats. And then once you have that done, you just do a little tiny science thread, right? So this thread's job is to look at a watch, say, okay, how long has it been since I ran an experiment? And it will look at its watch and say, okay, I need to run an experiment every 30 minutes, now it's time, so run the buzzer, wait for the rat to respond, and if it doesn't respond in 30 seconds, well, the experiment's a fail. And then to tie all this together and remember what happened, you create a data interface to sort of render your results and save your data. And finally, you just sort of load this all into a Bottle web server, set up some callbacks, and it runs. Okay, so you guys want to see code? Say yes. You have seen code today, right? People just don't talk. All right, so this is the main web server, and so this, I don't want to go on too long because I want to show you guys an actual demo of the hardware, so build some anticipation. So this is really, really simple. I just import the 4 modules I just talked about, and I'll go over those all in detail, but I'll give you the overview here. There's a simple JSON encoder for a message scheme that passes stuff over a WebSocket to the front end of the page. Then I have a pile of callbacks, right? And so these are basically there to run and say, whenever an event happens in hardware, call up and toss this either to a logging interface on Mongo or push it to the WebSocket. Once that's done, or with these in place, I basically create my objects, my 4 objects. And for all of this project, I use a really, really simple callback mechanism. So this is just lists of first-class functions being passed back and forth. So I say, like, hey, here's my protocol runner, run the experiments. Here's where you log your data. Whenever you get something that you want to save, like, say, a pass event or a fail event or a start experiment event, send it there. I also tell it, hey, whenever you get a pass event, say, call up the front end and send it there. And so I go through and I set all these events, right? So pass experiment, fail experiment. Similarly, from the hardware, I say whenever a button is pressed, whenever it comes up, notify the front end, log the data to the database, and also tell the experiment runner that, hey, a button went up, so if you're actually trying to look at an experiment, remember that. And so there's analogies for the buzzer and the feeder, and similarly for the camera on motion. So whenever the camera motion gets a motion update every once a second, send that to database and update stuff. Then you basically tell everything to start all your threads, and so you go through, and after this, it's a standard bottle web server. So set your routes for your images and your JavaScript and your CSS. I use Bootstrap in this case just to make it look pretty. Set up your error pages. Now to actually get the events to happen. So one of the things you want, right, is to have a controller. So you want to be able to click buzz and have the box buzz, or you want to click buzz in your web page and have the box buzz. So all I did is I set up a route. So whenever you post to this route, you just call the hardware interface and say buzz. And there's a little trick on how I do that so it works well. Similarly, on running the feeder, you just call this, you post to this feed event, and it'll dispense food. Pictures, same thing, and a lot of the stuff after this is pretty cut and dry. Like, this is a my data generate activity. So this generates your plot, right? That says this is the rat's activity over a day. Just simply call that method. It'll save a file to your image path, which is not great, but it's a quick and dirty way to get this done. And render the bottle template. Similar again for a pass-fail. We have some table stuff that generates statistics on every day's run, and a couple more just sort of fixed pages. Here's a little bit of meat. So this is going to be right here, where we actually set up the WebSocket to push data to the web front end. Finally, and this is just a little bit of a helpful thing, is that you set up a signal handler, so when you close down the web server, you shut down all the hardware threads. They're set in daemon mode, which should kill it, but it's usually good to help shut them down in a nice, clean, orderly way. So then we can also look at the hardware interface. So that looks like this. And this is super simple. Wrote it in an afternoon. Basically what you do is you initialize the thread. Like I said, you set it as a daemon so that it dies when you kill the web server. Then you have some pins to set. So on a Raspberry Pi, you have, I think, half a dozen or so, maybe 8 GPIO pins. So you set the GPIO pins to coils that are going to be used to run your stepper motor, or the pin that will be used to run your buzzer, or the pin that is connected to your switch. So I set all those up with the output, set all the ones that are output, the buzzer and the stepper motor, and I set the input for the trigger switch. And then I set some internal state variables. So the way this is all going to work is that whenever you want to dispense food or run the buzzer, you set a flag. And so when you set the flag inside of a main loop inside the thread, you just say, you count down. So you do it, we know roughly, this is not completely time accurate, but you say roughly 5 times a second, I want you to count down and keep running the buzzer. So you start at 5, you say, okay, I'm running the buzzer 5, 4, 3, 2, 1, and then you turn it off. And that's your thread. Along with that, I also set up some callbacks. So these callbacks are there to notify other either modules or the main app when an event occurs. So like whenever I dispense food, somebody can set the callback, which they just hand me a function. I say, set this callback here. And whenever I dispense food, I'll call that function and say, okay, I dispense food. And as long as everyone does this relatively quickly, it's not a big deal. So you can see that here. So when I call dispense, I basically check if the flag for dispensing is up. If it's not, well, cool. So we reset our step counter, we bring the flag up, and then we just call all these callback mechanisms. Similar for buzzing, same deal. This is where we set the callbacks. And this is where we actually set the stepper motor. So stepper motors are they're basically 2 pairs of coils, and you sort of alternate how the coils are running, and that causes it to step. So you need 4 pins, and you can build a stepper motor driver. So here I have basically a single step, where I say set this pen high, then this pen high, then this pen high. Those go through the amplifier and they step the motor. And I have a nice interface for the buttons. And finally, a shutdown mechanism, just that sets all the pens high. If this is just a good point for building stuff, if you're using, say, a Raspberry Pi or some other interface to build hardware, one of the greatest things you can do is run the IPython Notebook and bring all your GPIO pins in, because then you can interactively bring them up and down really, really easy. And as you're, if you have a circuit board or a breadboard or something and you're trying to debug what's going on, you can bring them up and bring them down and actually, put your multimeter on there and say, oh, yes, it came up. Okay, so it's working. So then you just run everything, and this basically checks to see if the flags are up, does the bookkeeping, and sends it on its merry way. And finally, there's the bit of logic for the buttons. So button presses are actually really easy. You're just looking for a high or low signal, but usually you don't want to detect high or low because those are fixed. What you actually want to detect is the derivative, right, going from 0 to 1 or 1 to 0. So I basically have a little method here that looks for that and then does the callbacks for button pressing. Okay, so let's now take a look at the camera interface. So the camera interface is again, super simple, same sort of idea, running the thread. In this case, I'm not really going to ask it for anything. It's just going to go run and take a photo once a second. And every time it actually gets a photo, it's just going to save it to a regular directory in the web server. And it's also going to calculate the motion between the previous frame. So this calculation right here, this calculate motion, basically what you do is you say, okay, here's the last image I took. So you have to initialize it, but you say, here's the last image I took, and here's the image I just took. And you literally take every single pixel and you subtract them from one another. If things are moving, if activity is going on, that difference will be big. If nothing's going on, if you have the same image, and if you have the same image twice, the difference is going to be really, really small. So all I do is I convert both the images, the previous one and the current one, to grayscale, subtract them from one another, take the absolute value, and then take the mean of that, and that's my correlate for motion or movement. I also do a little bit of temporal filtering, because if you do that it's a really rough mechanism. So if you average this out over a couple frames, you get much better results. Getting images off the Raspberry Pi camera is a little bit different than, say, a standard USB camera. What you do is you create a stream, and you basically pipe the PNG out of the Raspberry Pi into the stream, and then you can use NumPy to decode that stream and push it into a data buffer. And then you can then use that data buffer inside of the OpenCV2 bindings to either save the image, do some processing, or whatever you need to do. So once you have basically these two functions, get image and calculate motion, the main thread loop becomes super easy. Get an image, calculate motion, wait a second. Get image, calculate motion, wait a second. So how are we doing on time? Good? All right, so next. So here is where the science happens. And this is, I'm going to go through this really quick. So same loop primitive, same sets of callbacks. And the only interesting thing here is that I pass in the hardware too. So the hardware basically, or the hardware interface. And so all this thing does is it basically looks for two things. It looks at its watch every few minutes. It does this time diff. Says, this happened, run it. Or it's been this long, run another experiment. Or it hasn't been this long, so run another, or don't run another experiment. And if the experiment's running and the rat pushes a lever, then stop the experiment and record the results. And finally, we have a data interface. And this is super simple. It's just a connection to a Mongo database, and a bunch of really simple functions that shove data into Mongo whenever you call them. So it's just, and this is extremely primitive, but it's just log an experiment, log a buzz, and record a timestamp. To display the data, you basically go and you ask Mongo, hey, has it been, give me all the data for 24 hours that is just buzz presses, or is button presses, or just buzzes, or experiments. And to generate some of this for the user, you just go and query all that data and use matplotlib to render it. So just really simple. matplotlib rendering. Now, if you really wanted to be fancy, you should do this in JavaScript, but this is a Python conference, so let's do it in Python with matplotlib. The other thing you should know about using matplotlib is you have to set the back end. Matplotlib actually usually wants to run in an interactive mode, so you have to change this flag to get it to run correctly. Okay, so is that enough code? Are you guys done with that? You want to see some demo and have some fun? So where's my rat, my human rat assistant? All right, so I'm going to basically run some code here. This is on the Pi, so I've SS staged in. All right, so we're going to pretend that it's a regular day at my house, and I've left to go to work, and I'm sitting around, and why don't we grab a rat and just kind of have it run? Yeah, just walk around a little bit. It should run around in the cage. And so we will go to, all right. So we are now connected to the web server on the Raspberry Pi with the rat. Rat, will you push that lever right there? Why, thank you. So then a button press event came up through the WebSocket. And maybe we should, would you guys like to take a look at this rat and see what's going on up here? Oops.
Do we do something with the other rats or just this rat?
We can just do that rat. Oops. Oh, you're buzzing. An experiment's running.
Yes. Will
you hit the lever for me? Excellent. There we go. So live feed of the rat. We can also look at your activity. So caveat here, I just killed the MongoDB, so this is not all day. It's just the past couple minutes. So this takes a few seconds to render. But so this is just the activity of the rat over the past 2 minutes while it's been in here. We can actually revisit this in a second. We can also look at the experimental results. It'll buzz again here in a second, so hold on, and we'll have a fail. Okay, so you press the lever once, and it went once. Excellent.
Should I press it?
No.
Okay.
It runs once a minute. Well, I guess in the meantime, I will buzz it manually. I don't know, how far back can you hear that? Excellent. It's that annoying. I had to move it out of my bedroom. So I can also feed you. Oh, feed.
Thank you. Rat says.
Oh, yes. And we can actually see how you've been doing over the course of the day. So we can see how many times you've done correct presses and a number of times you've had bad presses. So today you failed 0 times, but you've passed twice. The total number of experiments is 2. 100% correct. Number of times we've dispensed food, the number of times you press that button, the number of times the buzzer has buzzed. And I can also see the correlate for your activity.
Can I mention my name is Peter? It
Sure.
stands for People for the Ethical Treatment of Rats.
Ethical treatment. Will you be my IRB? And so that's about it. You guys have any questions or? So this is all open software. I've actually put all the hardware too up on Thingiverse, so it is all free. Go fork it, fix it, mess with it, build something else. Excellent.
Okay, thank you, Katherine.
Yep.
So if you have any questions, there's a mic here up front, so please come and ask your question.
Yeah, thanks. That's very interesting. Is there something about the Raspberry Pi specifically that you decided to use that for, or you just have hooked it to a regular PC and done all this?
Excuse me? Oh, you certainly could. It's just it's a cheap piece of hardware. It's a $30 piece of hardware. You could choose a BeagleBone. You could run off a Minnow board. You could do any of that. You could run it on a web server, and it would be blazingly fast and wonderful. But I don't want to leave one next to the rat cage. Any other questions?
Yeah, I'd like to squeak with you about the design.
Okay.
You really don't need MongoDB.
What?
You really don't need MongoDB. You just need to write text files, right?
You-
Since you're keeping the picture as a separate object, right?
Yes.
It's not like you're dumping the picture into MongoDB or
Oh,
any of the
oh,
data.
certainly. There's like, it's completely lean. There's no reason really than to show some principles of, hey, I'm pushing this to a database. I mean, yes, you could get away with a text file and it'd be probably better, easier, more robust and a lot of other stuff. But I wanted to write some code that was actually a little bit, something that you could build upon to do something slightly more complex.
It's a nice project.
Hi.
I think that was my question too. Oops, sorry. But so tell us more about how did you put Mongo on there?
Excuse me?
How did you put Mongo onto it? You said it was hard.
Oh,
Did you
there's actually a couple tutorials, and it was pretty straightforward. You'll want to start out with a large SD card, and it will fail. You will not keep this data a long time.
Okay.
Or you need to replicate it across something else. But, you know, on a day-to-day basis, if you're replicating once a day, it seems really robust once it's running, but it seems like when the Pi comes down and comes back up, there seems to be issues.
And tell me again where we find the project online?
So it's all up on GitHub, and so if you, it should be on my blog here fairly quickly, but it's all on GitHub.
Okay, great.
Do you have the results of the experiment?
So we're still having, my friend who's doing the mechanical engineering, we're still having problems with this thing here. And these are actually really hard. The food hopper is really hard to build. I've been feeding them kicks because they're like kid tested, rat approved, or, you know. There's actually proprietary science blend sugar pellets that they normally feed rats. And those, aside from the box being $10,000, those might as well be $10,000 for sugar pellets. But getting that food to move through is actually, mechanical engineering is a lot harder than you would think it would be, especially when you're running off a 3D printer and trying to do stuff cheap.
Good luck.
But we'll hopefully have some shaping behavior here soon.
Cool project. One thing you might want to think about instead of Rabbit, just to keep it easy, is IBM has an MQTT queuing system, which is made for Raspberry Pi and Arduinos and stuff like that.
Yeah, there's multiple queuing systems.
Yeah,
actually,
so super light and
queuing systems for doing hardware. So Raspberry Pi is definitely not my preferred platform. I've actually been using ROS a lot for doing bigger real work projects. And I can't talk enough about how awesome ROS is. ROS is Robot Operating System. And if you guys have not played with it, go play with it, because it is awesome. It's awesome, actually. Any other questions? You guys want to go have beer? It's been a fun day. Cool.